Okay, so welcome back. Time to save the planet again. The aliens are back. They're going to destroy a city. We're going to have to do multiplication to placate them because we did addition before and subtraction before. So I started out doing some of this and I lost recording, which is kind of frustrating. So I'll do a bit more of it again. So the first one I did was multiply 7 times 5, which again, an enormously complicated sum to do. So I went in here, I did 7 times 5 equals 35. And control U, and it finds it in the database directly. So 7 times 5 equals 35 is already included in the metamath database. So I came back in here and I filled it in with great confidence that even when the stakes are super high, you can trust metamath to be correct. So that was that. And then I moved on to 164 times minus 197. So let's try and do that. And I think we need this. So we need 164. So let's have a new proof. Do not save changes. Yeah. Okay. So we have 164 times minus 197, I think it was. 164 times minus 197, and that is equal to, is equal to this. 32,308. 4 of those, and minus u. And again, that's how you write minuses in metamath, is to use minus u. And in general, all of metamath is ASCII characters. So each one of these is a different ASCII character to represent a math symbol. And not all of them are like kind of how you're used to in mathematics. So once you get used to reading metamath, it's really not too bad. But everything's kind of a little bit mixed up. So if you want to have the existence symbol, for instance, a set theory existence, that's E dot. And if you want to have the all symbol, that's A dot, capital A dot. But it kind of doesn't look the same because the all symbol is kind of like an upside down A, but it has to be written in ASCII, so they use these things. So anyway, that's how you write negatives. And let's see if metamath can do this. It cannot. It's stuck. Okay. So I think in order to make some progress with this, let's try and solve it without negatives. Okay. So if I could prove this without negatives, I think I'd be most of the way there, right? So we've done the multiplication, and then we just need to show that if you put a minus on the one side, you get a minus on the other. And I think super impressively for metamath, which is amazing, it knows how to use decmul-c, so decimal multiplication with carry, and it's just filled the whole thing in. I mean, look how much it's done. This is just incredible. And I'd really like to heap a lot of praise on the people who worked on this program. Like, I think Mario Carnera did a lot of it, and there's a lot of other people who've worked on MMJ2 too. But like, this is so impressive to have filled in all of this. I mean, this would take ages. Imagine trying to do this by hand, of finding all these theorems in the database and, you know, and putting them in exactly the right way so they fit all of the criteria. I mean, this is really good. And it's just slickly done that whole multiplication in one go. So incredible, incredible work by them. I'm really very impressed. Okay, so we have the multiplication done positively, but we just need to add the negatives in. And so I think if we do this, I think if we put minus u on both sides, I think it's fine. So if the minus u's are out the front, yeah, seems to be a bit unhappy with that, which I think is a bit weird because it says it's, oh wait, okay, yes. Put an exclamation mark in. I think the Americans call this exclamation mark a bang, I think, which I kind of like that. So you put it in, it's like bang, negeki. Comes and saves the day. So negeki basically is that if A equals B, then minus A equals minus B. And that's like a pretty straightforward idea. And now we just need to move this U, this minus U, into the bracket. But I think this is going to be a little bit more difficult than I hope it will be. So I'm hoping that it's enough to just take this and say, okay, this is equal to this, but with the minus U on the 197, which is what we want. Like that. And metamath is saying that with the result is saying if I can get this u inside the bracket, then it's happy that this minus u, which is the right-hand side here, and this is the left-hand side, then it can use ectree 3i to equate these three things. But it's not happy to just push that u inside. It doesn't seem to like it. And I think it's because it's something to do with the way that things are ordered. Like again, metamath, it's kind of amazing. It's kind of a beautiful system because it works on such an incredibly fine atomic level where everything has to be completely precise. So this, it has no idea. It says, I've got absolutely no idea whether that's true or not, and I can't find it. But I managed to have a look in the database. This is set.mmm, just load up in a text file. This is the whole database of proofs. And it does have molneg1, right? So if A is complex and B is complex, and natural numbers are all complex numbers, then you can have the minus out the front and then the minus in the bracket with the first term or with the second term. Okay, molneg2. So I think we should just use that. And again, that seems to be a very molneg2. So again, it's funny how it sort of goes from the sublime to the ridiculous, right? So like it's done this whole huge proof all by itself without any prompting. But then this is what throws it up. So we need molneg2. So I would suggest we want this to be this right-hand side, right? And I think we need to keep the implication. So this last bracket is part of this implication sign. So I think... Okay, so that's filled that in. Yeah. So this is saying, if these are complex numbers, then this thing is true, okay? But we haven't yet shown that they are complex numbers. So let's try doing that. We want, and it may have some stuff up here that can help us. Does it have 164 is a complex number? How close did it get? It's got 16 is natural. Don't know. Okay, well let's see. It can do the search for that. 164 with turnstile. The turnstile symbol, that one with the vertical line and the horizontal, just means this is the start of a proposition. Like this is the start of a provable statement. And e.cc, this is for the membership. So you know, in normal notation, that's like a sort of C with a bar in the middle of it. Here it's e dot. Okay, so let's see if it can do that. Yeah, loves it. It says it's used D7 and D8. So where did it come up with those? So it knows already it's got 16 and 4. Okay, and that's enough to construct up to 62164. And then it said, if it's a natural number, then it's a complex number, right? Or if it's a counting number, then it's a complex number. And let's have 370. What's the next one? 197. 19.cc. Okay. What just happened? I pressed the button and something really weird happened. Where did my thing that I just typed go? Okay, that is really weird. Maybe it's already got it somewhere else. I think sometimes it does that. And it sort of like deletes it and says, oh no, I've already done that for you somewhere else. And so I'll jump up to that level. Yeah, there we go. Okay, it's D19. So 197e.cc, it's already done that. So it's saying like, you don't need to do it again, mate. You've already done it. Like, you're drunk, go home. Okay, so 375. What I want, so this is saying, if this and this is true, this is the symbol for and again, in normal notation, that's just an upside down wedge, but in this, or as a wedge symbol, and in this, it has to be 2 slashes. If these two things are true, then this is true, right? So I'm just going to take this whole latter thing, and I'm going to say, okay, let's break that out. That's pretty ugly. Let's break that out without those. It doesn't need these things, because basically what it's saying is that if this and this are true, then this is true. And I've shown it, yeah, 164 is CC and 197 is CC, and therefore invalid first symbol. Okay, let's try that again. Yeah. Okay, so that was saying, I've proven both of these things, so therefore this statement is true on its own. And if this statement is true on its own, then this statement is true. Because I just swapped the order of them round. Eccomi will switch the order of them round. And then if this is true, then that's enough to get the minus on the inside of the bracket using 300, and so it can use 400 and 300 to prove the final result. So after quite a lot of messing around, this is a pretty long proof, huh? Look at all that. So the way the proofs are encoded is that this is a list of all of the names of the theorems that are used in the proof. So for example, so 6nn0 will be 6 is a natural number or a counting number. And then like 8 is a counting number. 7 plus 6 equals 13. Ovec theorem that we used. What were the last ones that we used? Yeah, ectree 3i, so that's here. Negeki, it sort of lists out all the ones that you've used. And then this is a compressed notation, which is basically saying the order in which you use these, okay? And it compresses it down into 26 ASCII characters, but basically it's saying, take your starting point and then use this, like use the first one, use the second one, then use the first one again, then use this, then use that, then combine those like this. This is the basic instructions for how it all works. But because it's generated a proof, we can be convinced that is right. And so we want to put this answer into here and then format it properly, because we're going to get the earth destroyed by lack of proper formatting. Like this. And we're correct. So that is really very good. So that's how you do multiplication problems in Wolfram Alpha. From Wolfram Alpha in metamath. And I want to just skip through a couple to see if I can find a really good straightforward multiplication question, because I just want to show how impressive MMJ2 is before we move on, really. Like one that doesn't have a negative in it, because that was what took all the time. I don't know why they've all got negatives in. I don't know why the aliens are being really very inconsiderate. Like, I guess I could... Is it 20 times 63? Is that large enough? What I would like is 2 3-digit numbers multiplied together, please. Just come on, Wolfram. Give me 2 3-digit numbers. Come on, you can do it. Don't be annoying, Wolfram. You know, I don't know why everything has to have negatives in. This is so irritating. All right. 85 times 203. Let's try that. All right. So what should it be? 85 times 203 is 17,255. All right. So look, let's have a new proof. No save changes. And let's have... So we're just going to put in... What was it? 75 times 203 is equal to this. I think that needs 4 of those. Yeah. And you just say, bang, MMJ2, can you find me the answer? And it just goes, chugging along for a bit, because it's going to take it a while to do it. And also sometimes MMJ2 will crash because you'll ask it something really big and it thinks it can do it, and it spends ages and ages searching through the database before deciding that it can't. So that might be kind of a hilarious place to end the video, is if I've managed to crash MMJ2 by asking it to do something too big. But yeah, I was just really impressed by how well it can look things up for itself. That often it can fill in, like that I showed you before, how it just did the multiplication. It just did it all in one go and filled in probably 20 or 30 steps of a proof, which is really good, which is really cool. Project's really coming along, and I think it's an amazing testament to Norm McGill, who's the guy who started it, and I think he died recently, unfortunately, which is a bit sad. But it's an amazing testament to his legacy that this project's coming along and it's great. They're working on a new proof system actually to complement this. Okay. So I don't think this is going to work because I think it's crashed. And I think the reason it's crashing, I think, is because it's trying to do something really big and it can almost do it. And it's sort of chunking through all these steps and it's doing 20 or 30 steps in the background. So I'll leave that there. We'll have to see if it finishes. I'll let you know at the beginning of the next video if it does. And otherwise, I will see you in the next one for, I think, having done the first 3, we're on to divide. And I think divide could be quite interesting. I don't know what theorems there are related to it. And I don't know what solutions it's expecting. Like, is it expecting decimals or fractions? Because in some ways with divide, what's 7 divided by 2? It's just 7 over 2. So we'll have to see what we can make of that. Anyway, hope you enjoyed it. I hope you had a good time. And yeah, see you in the next one. All right, bye.